Okay, so this is going to be the penultimate part of this lecture series, and we're going to be focusing on the phase space fluid. So the kind of knee-jerk reaction we've had when studying mechanics is to find the initial conditions and follow trajectories. But if we were to take a step back and imagine all possible initial conditions and all possible trajectories, we could actually do a lot more work with that, and a lot more to work with that in a more general sense. So imagine we have our complete phase space, complete with 2n dimensions for a system with n coordinates as per normal, and we were to fill this space up with a fluid, with each particle of said fluid being at each different coordinate, so each different momentum or position. Okay, and we can see how this moves accordingly to the system's equations of motion. So we would then have that the Hamiltonian of this system, so Q and of function of Q and P, will be some energy, and assuming the system is in time translation invariant, we can say that this energy is constant. And if we imagine that we have some, we'll take 2D space for now. So we'll say, like we had with the harmonic oscillator, we have, say, momentum and position going in one direction, so something moving along one axis. Well, this energy here would be as a function of Q and P, and so would draw out some shape, some general shape like this. But it wouldn't just draw out one, it could draw out an infinite number of them depending on where we start or so forth. So here's, say, a few examples. And the idea is that these are called contours. So similarly, if you've ever read a map going hiking or so, and we have contours that distinguish height or altitude. In this case, we have our contours that would distinguish energy. So each of these different shapes, these 2D shapes, represent a different energy. And if a particle is on one of them, so let's say we have a particle on this outer one here, because it has constant energy, it can only live on this contour. All right, so that's the whole idea. So when we had, say, in the harmonic oscillator, we had, I'll do this in blue. So we had that the energy, E, was equal to omega over 2 times P squared plus Q squared. And this would just be a certain scaled circle. So we can draw this circle like this. And once this particle would be set with a certain omega, P and Q, it would just live on this circle. So this would be, this circle, this contour representing the energy, it would live on that forever. And this is how we can graphically show conservation of energy in the phase space. Okay, so now we have an idea of what we mean by the phase space fluid, and that we'll put it aside for the minute and kind of focus on some math that we need to cover first. So if we imagine some random vector field, which we'll denote as, well, we'll say a velocity field. We'll say V, which is a vector, and is a function of x, y, and z. So it's 3D position coordinates. So if we had that in 3D, we can say here, we have the x, y, and z axes. Each position will have, so say we'll have down here, and go up a certain amount. Each of these positions will have an associated vector. throughout the entire space. So every single point in that space has a vector associated with it, which is pointing in a certain direction at a certain magnitude. So if you imagine like an entire space full of arrows pointing in certain directions, that's how we can kind of generalize a vector space, or in this case specifically a velocity space. So then if we have, say for instance, loads of these arrows moving in a certain way, in a certain pattern, all across it, we might want to mention, or we might want to figure out the kind of density of it. So let's say we want to see how much we can get it, or how many vectors will flow in versus flowing out of a certain area. So if let's say we draw some random cube here. And this cube has, it follows the equations or the inequalities. X naught will be greater than x, or less than x, which is less than x naught plus some dx. And same with y naught plus dy and z naught and z. Okay, so now that we have this cube being represented by these three inequalities, so we have that x, y, and z will range from, x will range between x naught and x naught plus dx, y naught the same, and z naught. That will represent this cube here, right? So if we kind of enlarge this cube, so we'll take this and we'll enlarge the cube in our vector field. We'll have, so our square here. Okay. Looking sort of like this, so that's not the best. Right, so we have different faces here, and these different vectors will be pointing in or along and flowing through one face. And we want to see that if it flows in through one face, will it flow out the same side? So if we have, say, this here as the x side, which flows from x naught to x naught plus dx, let's actually say that they come in from the x naught side and they come out the x naught plus dx side. So if they're coming in this way, and they'll be flowing out in this direction, what is the flux here? So when we talk about flux as in how the amount of vectors that are pointing in minus the amount of vectors that are pointing out, how much of it is actually getting transported through. Okay, and so we say that this flux we'll call phi, capital Phi here. And if we want to say just along the x direction, so the x naught, the face at x naught versus the face at x naught plus dx, we'll write this as a subscript phi sub x. And we'll say that this is somewhat proportional to, which is what this character here means proportional to. It's somewhat proportional to the negative change in v dv dx times dx times the face that it's on, dx dy dz. Okay, so now that we have our flux being related to our vector field here times the size of our face, etc., we're able to move on to thinking about the flux in general. So this gives us an idea of the inflow versus the outflow in the x direction, but we can also write that as the y and the z direction as well. Right, so this means that we can generalize this as phi in general being just the sum of these. So we'll get a minus, bracket out, dv e sub x times dx plus dvy plus dvz times dx, dy, dz. Okay, and now this is a very kind of peculiar way of doing derivatives. Not peculiar as it seems to be special, right? We're taking our different components of our vector field and we are differentiating them with respect to their basis component. So this comes up a lot, and we use something called the gradient operator, or in this case, the divergence operator, to denote that. So we denote our divergence with an upside down delta, or nabla, which so we'll call that our nabla. And so when we're using this, we can say that phi here is going to be minus. Now this particular use of nabla is called the divergence, which is nabla dot our vector field v, and then times dx, dy, and dz. But this here is our key component of what we're talking about, right? This is called our divergence, which is notated as nabla dot v. Okay, so now that we have an idea of divergence, which measures kind of the spread of particles, right? So we want our fluid to be incompressible, right? Just like in real life, which means we can't stretch it or compress it or anything like that, which means that the spread of particles must be zero, right? It can't spread anywhere because it must be constantly dense everywhere. Otherwise, that would be the same as compressing and stretching it in different areas. So this means that our flux here must be zero, which, given that it must be zero everywhere, means that if the fluid, if and only if, which is what we use this IFF for, if and only if, the fluid is incompressible, the divergence of the vector field will be equal to zero. Okay, so now we're going to head back to the phase space and use this information we've learned about divergence to kind of help us there. So when we were talking about divergence before, we had an x, and y, and z coordinate. But in this case, we're going to be in the phase space, and so we'll have 2n dimensions for every n coordinates. And so we won't be able to get around with just the 3. We'll have to generalize that a bit too. So in this case, we'll say that the divergence of this velocity field, or this vector field in general, but the phase space velocity field, will be equal to the sum over I of dv sub I, dv sub q sub I, dq sub I, plus dv sub p sub I, dp sub I, right? Because this velocity field is a function of all the QIs and all the PIs as well, right? Okay, so yeah, we have our generalized version of a divergence now, and let's just have a look at what we mean by V sub q sub I and v sub p sub I. So this might be just as simple as you'd expect. They're just the velocities of q sub I and p sub I in our phase space. So by this we just mean our time derivative of v sub q sub I, which is of course q sub I dot. And likewise, we have d dt v sub p sub I, which is p sub I dot. Now these two quantities you might recognize as being the quantities given from Hamilton's equations, right? So this means that we can rewrite these. So q sub I is going to be dv, or sorry, dh dp sub I, and p sub I dot is going to be negative dh dq sub I. Okay, so now we have our new expressions. We can put this back into the divergence. And so we'll get that the sum over I of d dq sub I times dh dp sub I. And we'll carry this minus through, and we'll get minus d dp sub I times dh dq sub I. Right, and if you remember from the beginning when we were originally talking about partial derivatives, we said that you could swap around the, given that everything is continuous and nice, like we usually assume, you can swap around the denominators or the variables you're differentiating with respect to in a second order partial derivative without any matters at all. So we then noticed that this ddq sub I and ddp sub I are both appearing just in reverse order. But because we now know that that's equal to each other, we know that this will all cancel out. So we'll get that this is equal to 0, which is exactly the criteria or the criterion that we needed to know that this fluid is now incompressible. So that's how we know that the phase space fluid is compressible. And this is called the Gibbs-Louisville theorem. Okay, to give a quick example of this, we're going to take, say, something with the Hamiltonian equal to p times q, right? Okay, so now the equations of motion of this, we'll get that dh dp is equal to q, and which is equal to minus p dot, which is equal to q dot, and dh dq is equal to p, which is equal to minus p dot. Okay, so that means our equations of motion, therefore, will be q dot equal to q and p dot equal to minus p. Now we can start solving these, okay, so let's, instead of using dot notation, we'll go back to using our fractional derivative notation. So we'll say that dq dt is equal to q. And we're going to be able to solve this differential equation by bringing dt over, well, effectively bringing dt over and dividing by q and then integrating on both sides. So we'll get that dq over q is equal to dt. And now we'll just have to integrate both sides. So we'll get, say, from some q naught to q, and from some time equals 0 to t. The antiderivative of 1 over q with respect to q is going to be the natural logarithm, so ln, of the absolute value of q, evaluated between q naught and q, and then the integral of a constant, or just 1, will just give us t. So this would be the natural log of the absolute value of q minus ln of q naught, which is equal to t. By our logarithm rules, we can combine these into ln of q over q naught, which is equal to t. And by exponentiating both sides, we'll get that q over q naught is equal to e to the t, or that q is equal to q naught times e to the t. Okay, so this is how q, as a function of time rather, will grow. Okay, and now we can do the exact same with our p, and so we'll find that dp dt is equal to minus p. And so following the same steps, we'll get that the integral of dp over p from p naught to p is equal to the integral from 0 to t of minus dt. And so likewise, we'll find ln of p over p naught is equal to minus t, or that p will be equal to p naught times e to the minus t. Okay, so now that we have our q of t, so our position as a function of t, and our p of t, we can see that q of t is growing, or is increasing exponentially as t goes on. And similarly, p of t is decreasing exponentially as t goes on. And so when we vary t in this way, we'll see that as q grows, p shrinks. And so our total energy here, our total Hamiltonian, or energy given by our Hamiltonian, will remain the same throughout time. It will remain conserved. Our energy will remain conserved. Okay, so just before we finish up talking about the phase-space fluid, we're going to motivate something called Poisson brackets, named after a French mathematician. So imagine we have some function moving through the phase space. So this could be kinetic energy, potential energy, the Hamiltonian, etc. But to keep it general, we're going to just use some function f of qi and pi. And we're going to take its time derivative, okay? So we'll say that f dot is going to be the sum over I of df dq sub I times q sub I dot plus df dp sub I times p sub I dot. Okay, and now we can do what we've been normally doing, and we can sub in Hamilton's equations for this qi and pi dot, or qi dot and pi dot, and we'll find that this is then equal to the sum over I of df dq sub I times dh dp sub I minus df dp sub I times dh dq sub I. And now we can kind of see that this is, that's the time derivative of f. But we can kind of see the kind of symmetry in this, right? So we have the function differentiated with respect to q sub I times the Hamiltonian differentiated with respect to p sub I minus the function differentiated with respect to p sub I times the Hamiltonian differentiated with respect to q sub I. So this symmetry we can define as kind of what we call the Poisson bracket. So if we take some general functions f and g, or f and g, we say that the Poisson bracket, which is given by these curly brackets, of f and g is equal to the sum over I of df dq sub I times dg dp sub I minus df dp sub I times dg dq sub I. Right, so this is how we define our Poisson brackets. And then if we look back to our time derivative of our function f here, we can see that we've replaced g for our Hamiltonian h. And therefore, we can write that the Poisson bracket of f, which remember we've kept as a general function, with the Hamiltonian h is equal to the time derivative of that function. Which means if we take the Poisson bracket of any function operating in the phase space with the Hamiltonian, it gives us our time derivative of that function, which is a really simple equation or relation, but is massively important. And this idea of symmetry or this kind of notation is not just found here. It's also found in the likes of quantum mechanics and such. So this idea developed in, I think, the 1800s, really made a lot of life simpler down the line. And we'll explore more of this in the next lecture, where we'll talk about Poisson brackets completely.